All right, this is lesson 1.2. We're going to be talking about inverse functions today. I'm going to skip over this. All right, so an inverse function is a function that undoes the actions of the other function. So here's a function, f of x equals x plus 8. So whatever number you input into that function, maybe say we input 7 for x, the function will add 8 to it. So we would maybe get an answer of 15, and that's the output of the function. Those little arrows are going to drive me crazy. Oh, see, I can't. Ah, we got a new smart system. It's making me crazy. Okay, so the function there was to take a number x and then add 8. So the inverse function should undo everything that original function f did. So if it started with something like 15, it should undo and take it back to 7. So the inverse function, and we notate it like this with a -1 symbol, so we would read that as f inverse. So f inverse in this case would be to subtract 8. Now the trick about inverses is that it shouldn't just work for one value, like say 7. It should work for any value. So let's try this out with another value. What if, say, we input, let's say we input 11. Well, if I take that 11 and I add 8, I get 19. So the inverse should take 19 and get me back to 11. And you can see that does work. 19 minus 8 is 11. And if you found a true inverse, it should work with any input. So that's what an inverse is. An inverse undoes everything that the original function does. So in class we did a couple practices, but I'm going to skip through well, maybe we'll do a couple. So this one is the function takes an input and multiplies it by 3. So in this first example, if we put 7 into this function, it becomes 3 times 7, which is 21. If I'm trying to undo that, I want to start with the 21 and get back to 7. Well, the inverse function in this case would be x divided by 3. Or you could write it like this, but in Math 3 we would prefer this notation. Another way you could write this is 1/3 x. This one's kind of interesting. If you take a 7 into this function, it's 1/5 of 7. So that's the same as 7/5, or you could write it as a decimal if you really wanted to. 1.4. And so the inverse of that function needs to take that 7/5 or that 1.4 and turn it back into a 7. It's interesting maybe to note that timesing something by 1/5 is the same as dividing by 5. So to undo this function, its inverse would multiply by 5. So you kind of can see what inverses do. All right, so an interesting thing happens when you look at functions and their inverses graphed. Now you might not be familiar with how to graph some of these functions yet, and that's okay. But each of the graphs shows the original function in a solid line, and its inverse is the sort of dashed line. So I don't know if you notice, these instructions here say to graph the line y equals x. That's a diagonal line. And if we graph the line y equals x on each of these, if I can draw a straight line, what do you notice? Oh, that one's a little crooked. And hopefully as you look at those, something sort of jumps out at you, and it is maybe the word reflection. if you remember that word. Sometimes people don't come up with that word, but they can sort of see that the inverse is the mirror of the original function, and that is true of all functions and their inverses. They are reflections of each other, and the mirror, so to speak, or the line of symmetry is the line y equals x. It's a diagonal reflection. So we wanted to write a couple of points down, and we're going to first work with this original line right here. This original function is f of x, and if we list out those 5 points on our table, we have the point -5, -5, and that next point is -3, -4. So remember, when you're writing a point, it's the x value and then the y value. This one would be 1, -2. This point right here is the point 5, 0, and the last point is the point 7, 1. So that's a table of that function f. And now if we do that same thing with the inverse, here's the inverse. We want to list those 5 points. We'll start here. So we have -5, -5. The next point is -4, -3. The next point is -2, 1. That's right here. And then we have 0, 5, over 0, up 5. And the last one would be 1, 7. So that's a table of the inverse. So looking at those two tables, do you notice anything? You might notice that they are also sort of mirrored from each other. The x coordinate on that first table becomes the y coordinate on the second table, and the y coordinate, or the f value of that first table, becomes the x value. They sort of switch, if you will. And remember that these are y's. We write the function notation, but they're y values. So an inverse and a function has that property, like whatever points are on a function, if you switch the x and y values, that is one of the points on the inverse function. So for any function, we want to be able to find its inverse function, and we need a procedure because we don't want to have to graph every single thing. So we want a way to just start with a function like this one, f of x equals 1/4 x plus 1. That's the equation of a line. We want to be able to start with that function and come up with, through a process, the equation of its inverse. So we want to find, in this case, f inverse. So remembering that the domain and the range of a function and its inverse are switched. Those x values and y values switch for a function and its inverse. So to find the inverse, we're going to use that property. The first thing we're going to do is we're going to not use function notation. We're going to actually put y in our equation for f of x. And then we're going to physically switch the x and y. That is, wherever you see a y in an equation, you're going to put x, and wherever you see x, you're going to put y. Now, everything else in the equation stays the same. The only thing that changes is y's become x's and x's become y's. So we rewrote the function using y. We switched the x and y. And now to get that final inverse form, we just need to get that y by itself. We're going to just solve for y. So in this case, if we're trying to get this y by itself, we need to peel back all these other layers and move them over with the x. So we want y by itself. The first thing we want to do is subtract 1. So now we have x minus 1 equals 1/4 of y. Well, 1/4 of y is the same as dividing y by 4. So to undo that fraction, We just want to multiply both sides of our equation by 4. Now be careful here, you have to group that x minus 1. We want to multiply this whole side of the function by 4. Not just the x, not just the 1. We want to multiply that whole thing. So when we times by 4, those 4's cancel out. And so we have y equals, and over here we have 4 times x minus 1. Now typically you'd want to just distribute that 4. So we'll have 4x minus 4 as we multiply that out. Now this thing that y is equal to here, that's our inverse. Our last step is just to write it in proper inverse notation. So we have f inverse of x is equal to 4x minus 4. Now, to be honest, it's not a real deal breaker if you left it like this. It is probably considered a little more proper to multiply it out. But it's not the end of the world if you forget that distribution. All right, so that's our first example. We'll go through 2 more just to make sure that we really have that procedure down. We want to find g inverse in this case, so our original function g of x equals 2x minus 3. So we'll change that notation to y. Sometimes you just like put the y there so that you can save writing if you want. We're going to absolutely just switch that x and y because that's what an inverse is. It's like working backwards. Switch that x and y. So we have x equals 2y minus 3. And now we just want to solve for y. So we'll add 3 to get x plus 3 is equal to 2y. And our last step to get y by itself would be to divide by 2. Now make sure you divide that whole quantity by 2, not just the x, not just the 3. That whole quantity is divided by 2. Okay, so that is our inverse. X plus 3 all divided by 2 is our inverse. There's a couple ways you could write that. You could just leave it like that. That's perfectly acceptable. If you wanted to, you could say it's 1/2 x plus 3/2. You could write it like 1/2 times x plus 3 if you want. So there's a few ways that are all really pretty much equivalent. Whichever one you fancy is fine with me. And let's try one more. This one has kind of a tricky fraction to work with. So our original function h of x is 5/7 x plus 1. And we want to find h inverse. So this is y equals 5/7 x plus 1. We want the inverse, so we're going to switch that x and y. So this becomes x equals 5/7 y plus 1. So we want to solve that for y. We're going to start by subtracting 1. So we get x minus 1 equals 5/7 y. Now, 5/7, a fraction like this, often gives people a lot of trouble. You can take care of that fraction in 2 steps if you want, or you can take care of it all at once. So this divide by 7 right here, that's just saying divide by 7. So the way you would undo that is to multiply by 7. I'm going to do that step first. So this left-hand side, if I distribute it, becomes 7x minus 7. The 7's over here cancel, and we have 5y. And then our final step, as we're working towards getting y by itself, is to divide by 5. So we have y equals 7x minus 7 over 5. This is our inverse function. That's a fine way to write it if you want. I'll write a couple of the different ways you could write it over here. So you could leave it in that form. If you wanted, you could put that divide by 5 with each of the terms like this. And if you really, really wanted, you could do something crazy and write it like this. Those would all be okay. They all mean the same thing mathematically. So that inverse procedure, we are going to be practicing a lot this unit. So you'll get a lot of practice with that. All of the ones we were doing today were lines, but we'll be talking about some other types of functions later on in the unit. So practice that procedure. The assignment is just that one side of the paper, and let your teacher know if you need any help with that. Thank you.